So welcome everybody to this tutorial on the data reduction for scattering experiment. So the tutorial this afternoon, well, the slide I'm showing is the slide from this morning. It's related to, it was related to the tutorial of this morning, but I'll quickly go over the core principle of PiFi. But the idea this afternoon is that we discuss a bit about some advances on the separation of signal coming from the background and Bragg peaks mainly. And we'll see how this can be used for several applications. Maybe the first one is the one that is already used, for example, in diffraction tomography or on things like that, where you want to get rid of Bragg peaks into your data, and you're recording some smooth amorphous signal, sometimes a SAC signal, and the Bragg peaks coming from larger crystallites in your system is creating some disturbance in your data analysis. So that's one application. The second application is to extend this further, but instead of recording the background, we like to record the Bragg peaks, and this has an application for serial crystallography, at least in the way it's performed. It will be performed at ESRF on the beamline. So I'll present you the ID29 beamline. And the last part is about the processing of serial crystallography data. Maybe, I don't know if some other people are willing to attend. Maybe the easiest is to have a round table so that everybody introduces himself. So I'm Jérôme Kiefer. I'm the main developer of PiFi. I've been working on this for almost 12 years now, and yeah, I'm mostly involved into reduction of powder diffraction data and reduction of small angle scattering data. And so the application to MX is pretty new to me. This is why this work has been coordinated and validated by Nicolas. So maybe Nicolas, you can present yourself.
Yes, thanks, Jérôme. So I'm Nicolas Coquel, and I'm a crystallographer. I don't know, within the last 7 years, I've been performing a serial crystallography experiment at ESRF and other X-FEL sources. And I've been at ESRF for a bit more than 6 months now. And as Jérôme mentioned, we've worked together to use PiFi environment and recent development on GPU to perform heat and peak finding using Jérôme's algorithm.
Could the different attendees introduce themselves, please?
Hello, everyone. My name is Tatiana, and I'm a master student from Utrecht University, and I participated workshop this morning. So this is, I don't know anything about serial crystallography, so I'm interested to listen about this topic and find out more.
Okay, thanks. Alexander?
Hi, everyone. I'm from CFL, or from Henry's Chapman Group. So I'm interested in serial crystallography and what you do to compress data.
Okay. Welcome, then.
Hi, my name is Carolina, and I'm a doctoral student in Vienna at POCO. And we did some experiments at ID13 in 2020, and also this year some experiments are planned. And we do research on spider silk. So I already use PiFi and some scripts, but I still struggle with some things, but I have some experience, but not that much.
Okay, thanks. Mohamed Fares, please.
Yes, I am Mohamed, postdoc at ESRF, and I'm interested on process analyze diffraction in Bragg peaks, and you want to get it out of the background, and it's interesting to see how to do it using PiFi.
Well, I'll try to present you quickly PiFi. So I'm sorry for the two people who were already here this morning. It's the same slideshow. I'll try to go through quickly. So PiFi is initially a piece of software for doing data reduction for scattering experiments. So, well, I want to introduce you X-ray scattering. If you're here, you already know about powder diffraction, about small angle scattering. And basically, PiFi was done to transform an image like this into curves like this. And yeah, we'll go a bit in depth on how this is done. In order to perform this transformation of the image recorded by an X-ray camera and get either powder diffraction pattern or a cake image, as it's called, we need to know the geometry, and to perform the geometry, PiFi has some calibration tools that are able to localize the position of the detector with respect to the sample and the incoming beam. So PiFi is written in Python, but most of the numerical intensive part is done with C or C++ and compiled. PiFi does not only do azimuthal integration, it also performs all the previous processing steps that are needed, and one of the most important one is the pixelwise correction. So, for example, dark current subtraction. So if we have some raw signal coming out of the detector, if we have an integrating detector, we are likely to perform some dark current subtraction and flat field correction, which is this F at the denominator. But we need to correct also for the solid angle subtended by every single pixel, correct for polarization, parallax effect. I0 is some constant which depends on the incident flux. But well, this overall is the corrected intensity is some signal divided by some normalization. And usually when we perform azimuthal averaging, we consider that we are doing the average, the arithmetical average of the corrected intensity, which is not correct. Actually, we should perform the weighted average of the signal weighted by this normalization factor, and this gives this formula. So if we consider there's no pixel splitting, and one azimuthal beam is here, this curve, this area in red or pinkish, one would consider only the pixel which are marked in blue and account for those ones. And if we perform pixel splitting, we may have something that is a bit more precise, and yeah, and we will have this parameter Ci, which is the fraction of area of each pixel that contribute to every single beam. So here is the average, here is the uncertainty related to the pixel intensity, and if we want to have the uncertainty on the value of the mean, we have to divide roughly by the square root of the number of pixels contributing. But in the formalism of the weighted average, it gives this formula, which is slightly more complicated. Okay, so in PiFi we have images which are 2D array, NumPy arrays. We have this core object which is called azimuthal integrator, we'll see a bit today, which contains two main functions, which are integrate 1D to perform the 1D integration, integrate 2D that performs the caking of the image. And we will discover a couple of new ones, which are the one to perform sigma clipping and other treatments that are not as much advertised, but are very powerful, as we will see. The detector object in PiFi is responsible for calculating the pixel position, so the center of each pixel or the coordinate of the corner of the pixels. It also stores the mask for invalid pixel, and detector can be saved as HDF5 file, but we won't dive into this more today. And the geometry is roughly the position of the detector with respect to the sample position and the incoming beam, and the geometry is usually saved as a PONI file. We will see this later on. The geometry used by PiFi is similar to the one used in SPD, which is another program written by Peter Böseke, who inspired me. Basically, you have some incoming X-rays like this that hits the sample at a position which we call the origin. And if we follow the incoming beam, we hit the detector or not at a position that is the beam center. And but the beam center is not the origin in the geometry of PiFi. The origin is the origin of the detector is rather the point of normal incidence, which corresponds to the orthogonal projection of the sample or the origin on the detector. So orthogonal projection. And yeah, the good thing with the point of normal incidence is that it exists even if the detector is tilted by 90 degrees. And we have then 3 rotations to define the tilts, so rot 1 and rot 2. Rot 3 is a rotation along the incoming beam, since the system is most of the time or usually independent of this, so except maybe the polarization effect. Rot 3 is usually not refined. So to perform the calibration, we need the detector, so the geometry of the detector, the mask associated to the detector. We need a reference sample that we call calibrant, which is lanthanum hexaboride often, or ceria, or other calibrants, and the energy or the wavelength of the radiation that has been used. And this allows us to determine the distance from the sample to the detector, so the orthogonal distance, as well as the projection of the sample of the origin on the detector at PONI 1, PONI 2, as well as 3 rotations, rot 1, rot 2, and rot 3, which is usually kept at 0 because the system is invariant by rotation rot 3. So how this is performed: we extract group of peaks, we assign them 2 ring numbers, we perform a least square refinement of the geometry, and we validate the geometry. So this was seen this morning. For the integration, basically we consider each pixel of the detector. Each pixel has 4 corners, which have each of them 3 coordinates. So we expand this to have the coordinate, let's say x, y, z, of every single pixel of the detector. Then we perform the translation, so put the detector at the proper distance, offset to the PONI, and then we perform the rotation around the sample. This allows us to calculate the radial position, usually in 2 theta or q space, and the azimuthal position for each corner. And then we perform the histogramming. So we assign each pixel to 1 or multiple bins, and we account for the intensity of this pixel into the given bins. So this is done with histograms. So histogram of bin position weighted by the intensity, and another histogram weighted by the normalization. So I remind you that this corresponds mainly to the solid angle, to the flat field, and polarization effect, and so on and so forth. And at the end, we return the average, the azimuthal average, which is the sum of intensity divided by the sum of normalization. So this is an example of how it's done in Python. It's a bit out of the scope of this tutorial. Just a reminder that we need to go pretty fast. This sketch provided by the Coherent Imaging Group from UCLA has put in parallel the increase of computer speed, taking the fastest computer in the top 500, and the brilliance of synchrotron sources versus time. And in vertical axis, we have some logarithmic scale. And the important thing is that the brilliance of the X-ray sources increases much faster than the computation speed of the fastest computer. So we need better algorithm to perform the analysis of the data in order to keep up with the data deluge that are provided by the new detector. So here we have the speed of the latest detector available at ESRF, and so basically Eiger 2 is operating usually at 2 kHz. Jungfrau is expected to operate at 2 kHz, and with the case of Eiger with limited precision, we can go up to 20 kHz. Anyway, we have a physical limit at ESRF, which is that we are limited to 2 GB per second and per detector. This is the limit from our file system, and we cannot go faster for now. So the conclusion from the previous slide is that the gap between computing and what the scientists would like to do and what the scientists can have is growing. So all the previous programs, Phi2D written in Fortran, SPD written in C, or Foxtrot written in Java, they were all using the same algorithm, and this reaches its maximum speed. And in PiFi, we suggested to change the way this calculation was performed using some matrix multiplication, because it's a linear transformation. So we redeveloped the azimuthal integration using a sparse matrix multiplication. And well, this was described 10 years ago at EuroSciPy. And this is a snippet of code explaining how to do this in with NumPy. So we get a 5x extra speed up using a single core versus histograms. In this tutorial, we will only speak about sparse matrix multiplication because it will provide us with a very convenient way of having for each azimuthal bin which are the pixels which are contributing, and we will abuse this representation, and this will be in the second part, where we will discuss about discarding pixels, considering them Bragg peaks or not, and so on. So we'll right away forget about histogram, even if it's easier to understand. It has a lower memory consumption, and it's faster to initialize. We will be working with very large data sets, and we need this sparse matrix representation of the transformation. So here are some benchmark about the speed that one can reach with PiFi. That's the previous version of PiFi, but it doesn't matter. Using histograms, you reach 50 frames per second with a 1 megapixel image. So here, in horizontal axis, you have the image size from 1 to 16 megapixel, and the number of frames processed per second in a vertical axis, and each color represents a different algorithm. So this blue and orange curves correspond to histograms, so serial algorithm. The green and the red curve here correspond to some parallelization with a sparse matrix multiplication performed on CPU, so 6 cores with this computer, 1 socket, 6 cores, and we see that it's already much faster. And if we switch to a GPU, we can reach more than 500 frames per second in 1 megapixel images. And if one considers the latest computer that we have today, it's around between 1,600 and 1,800 frames per second. So the curve will be like this. So I didn't take the latest computer to perform the benchmark, but this is just to give you an idea of what we are able to do. Moira effect, that's something I just like to mention, is that if we don't have pixel splitting, we have some Moira pattern appearing. And basically in this whole tutorial, we will work without pixel splitting because I suspect it would make the calculation, maybe there are some bugs if the pixel splitting is activated. But yeah, pixel splitting allows to avoid those Moira patterns, and the cost to pay is that it creates cross correlation between bins, and this is something we definitely not want when we are treating data in serial crystallography. So PiFi has 3 pixel splitting schemes integrated, so without pixel splitting. So the simplest, the one called bounding box, that was very popular. So the pseudo pixel splitting is now deprecated. It's a shrink down of the bounding box method. This is what was used in Fit2D. And now we have the full pixel splitting in 1D, 2D, considering the just each pixel to be made of polygons with, for example, here 3 edges. Here we have 5 edges, and so on and so forth. So we consider each pixel as being a polygon. Well, pixel splitting has an impact on the integration speed, but we'll skip this. So this is the demonstration that the calculation should be performed, the intensity should be performed after during the integration, not before. So yeah, a second warning that pixel splitting creates bin correlation, and it has an effect on the precision of the propagated uncertainties. So the different layers in PiFi, so we have several tools to perform the integration using graphical user interfaces application, but we'll be more interested in this tutorial about the Python interface, so azimuthal integrator, and how some rebinning and histogramming engines work in PiFi. So this will be done using Jupyter. We'll be at the maximum of flexibility and the minimum ease of use, because yeah, it will be some hardcore stuff. And so the balance for now, it's really focusing on performances, and yeah, it's an advanced tutorial. About project management, well, PiFi runs on Python 3.6 to 3.10. It's free, fast, and portable. It's MIT licensed. This means that it's compatible for business. It's compatible with GPL code. I know that most of the code running on X-Files is GPL, but we have chosen a much more liberal license that allows companies to use our code. Well, we have about 20 direct contributors to PiFi, most of them from ESRF, so paid by ESRF, but we have also some help from other synchrotrons, Soleil and SLS2, Petra 3, the European X-File. We also have some industrial contributors from like Xenox, and I think it's worth mentioning because, well, we are open for business, but we have also feedback from business. And I know that PiFi is used by something like 50 other projects in many X-ray sources around the world, to name a few. But yeah, it's one of the numerical engine that is the most widely used for this kind of application. I personally try to avoid compromises, so there are things that are complicated in PiFi. I'm sorry. We try to do our best to make things correct. It's not always possible. It's not always possible to have it right now and correct. This means that that things are likely to change. Well, I just I put some deprecation warning or indication that the behavior is likely to change, and usually when I perform this, it's to correct a bug, a numerical bug, or something I didn't get correctly done in the first time, in the first time I implemented it. So, well, I'm performing like this because I consider that science does not suffer approximation. We need to try to go to and do the best. So the user community around PiFi, we have about 150 people registered to the mailing list, so PiFi at ESRF.fr. So the mailing list has a pretty low activity. 1/3 of the user are coming from ESRF, 1/6 from the rest of France, about as much from Germany, and the rest of Europe is as large as Germany, and then we have the rest of the world and some email addresses. I don't know where they come from. If you think you found a bug in PiFi, or maybe you'd like to see some added feature, the best way is to discuss this on the GitHub issue tracker, which is available here. And yeah, the reason to choose PiFi, well, we focused on speed. Speed is very important, but not more important than correct results. That's one thing that is a core importance. We've been the first one to describe sparse matrix multiplication to perform this integration. All computationally intensive code have been ported to C or C++ and to GPU via OpenCL. This means that we have several implementation of all compute intensive kernels. We are able to realize some validation between implementation and so on. Not all other programs have this ability to validate. We are the only one, I think, that are able to use GPUs. Well, and PiFi has been designed to be hackable, so we have several integration spaces that exist. You can just flip from one to the other by just changing one parameter. The geometry used is extremely generic. It works for SACs, for wax, for moving detectors, for curve detectors. Well, we're very versatile. Most of the detectors are already defined. Maybe it's not the case for XFELs, where the detectors are different, but I'd be happy to help you define your detector if you need. For the calibration, we have a very nice user interface thanks to Valentin Valls. And well, with the SELEX collaboration, we are more than one person to maintain the code. So yeah, SELEX was mainly about user interface, GPU computing, and scientific data analysis, so multi-threaded implementation of some core algorithm. Okay, just to give you an idea of what SELEX is about, those are all the graphical user interfaces and all the program we have developed within 3 years. So PyMCA is a spectroscopy, scanning spectroscopies. PiFi is about diffraction. Moira is about tomography. XOX is about current imaging. Crispy is about Xenos. Well, there's really a lot that has been done, and we we all use the same widgets, which makes things easier for our user because they find the same widgets from one application to the other. So this is a view of a 3D view of an experimental setup with a detector that has been, let's say, opened to let the X-ray go through. The image coming out of the detector looks like this, and we see here that the gap is closed. Here we see that there's actually a hole in the middle of the detector. Well, we manage highly tilted detector. We have a nice calibration tool. We start to have some calibration tool using Jupyter Lab. And yeah, I'd like to acknowledge all the people who helped me for PiFi. Mainly Valentin, so the guy who designed all the Qt part. Loïc, who's helping me on the Jupyter Lab part. Thomas, Armando, Claudio, those are for the SELEX collaboration. Plenty of beamlines of ESRF asked for new features and provided manpower to work on it. So we had contribution of several people from different synchrotrons, especially Fred from Soleil, Clemens, who has been at APS at European XFEL, and he's now at Freiburg, I think. Phil, who's moving from Marseille to Chicago. And I'd like to thank the Link Scheme grant, who provided us with 3 engineers to work on the GPU side. With this, I did something pretty quick, but I guess you have some idea what PiFi is about. And you may wonder, what's the relationship with serial crystallography? Was I clear? Do you have any question on this first part that I tried to make pretty quick because, well, yes, Alexander?
Yes, thank you very much. It was a nice introduction. Just a couple of questions. First of all, I didn't understand which Eiger do you mean talking about 20 kilohertz? 1 megapixel maximum speed, as far as I remember, 2 kilohertz in 16-bit mode.
It's an Eiger from PSI. So just
okay,
the chip,
special one.
just the chip with specific electronics, with reduced, I think they are working in 4-bit mode, something like this. Well, very, very limited precision. And this is used for XPCS. So
okay, so
not exactly
some custom Eiger, right?
Yes, it's a custom Eiger. I don't advertise the Eiger 2 generically to be operating at 20 kilohertz. It's one module, it's one specific beast.
Perfect, thank you. So talking about geometry, you have shown this like example with moving panels. So
Yes.
do you save geometry for each panel in H5 file, or how do you save
How it's
geometry?
how it's done usually, no, we share the wool detector into one file. And later on, each pixel is placed at, well, there's no notion of panel, let's say, in PiFi. We have one detector, and within one detector, we have pixels, and each pixel has a localization in space.
But do you have constraints that some pixels like correspond to the same panel? So therefore, there are some constraints in movement.
No, this is done when we were, for example, this detector, we had the metrology from all 10 panels, 2, 5, yeah, 10, we have 10 panels, and we had the position in space from each 10 panels, and from this geometry we build the position of each pixel in space, and this is saved in one HDF5 file that is used later on.
But I mean, if you change geometry, physical geometry of the detector, for example, you incline one panel, how
Yes.
can you modify your geometry to take this into account?
Basically, you cannot. This detector is there's no, for example, there's no translation stage on this. So
okay,
there are a few screws that locks the panel, and if you unscrew, you need to restart the calibration procedure. So we perform the calibration procedure each time the detector is modified. We save the detector geometry, and we use this detector geometry. But usually we avoid unscrewing the panels and yeah.
But actually, one more question related to this image. For example, if one of those two moved panels is not just
Yes.
moved, but moved and inclined, let's say around the red line, you can't calibrate it with rings.
No, it's not calibrated with rings. It's calibrated with so this is one single piece of silicon, which is mounted on top of an ASIC, and the ASIC has specific markers that are validated with an optical metrology tool. So we have
optical metrology. Okay.
Yes, we have 3 control points per panel, as you say. And with this, we are able to calculate the position in space. And yeah, the calculation is done once for good, and unless we unscrew.
Yeah, if you have optical metrology, there are no questions here. Sorry. Actually, one last question. You mentioned that this geometry file is quite big. So for 16M, it's like almost 1 gigabyte. So you have to apply this 1 gigabyte file to every pattern. Isn't it slowing down your calculations?
No, because this is reduced in the sparse matrix format later on. So basically, all the calculation is done beforehand. So we take, if we have a 16 megapixel, we take each of the pixel one by one out of the 16 million. We take the 4 corners and so on. We perform the translation rotation in space. We distribute the area of the pixel to the different bins if we perform pixel splitting. And this is recorded in the sparse matrix, the CSR matrix that we are using later on. And after this, we only remains this sparse matrix, which is pretty large, but we can do very interesting things with it.
Okay, thank you.
This is what we will see with the sigma clipping part that we'll introduce later on. Are there other questions? Maybe you want a small break?
I don't know. I was off for a few minutes. There was a question in the chat from Carolina. Did you see it?
I didn't see it. Where is the... Oh,
is normalization to incident beam intensity already done by PiFi?
It can be done by PiFi. You need to provide it.
But it's not automatically, when I do 1D or 2D integration, it's not automatically done. I have to...
Well, yeah, I see the question. No, it's not automatically done because there's no automatic, well, the incoming beam normalization depends. Do you want to consider the intensity of the storage ring? Or do you want to consider some monitor that is on the path? Do you want the incident beam or the transmitted beam to be, well, do you want your signal to be normalized?
Yeah, the incident beam. But it was just a general question if I have to concern it separately or if it is already included, but I see.
The code exists, but it needs to be properly activated.
Okay, thank you.
Which sometimes is not easy.
Yes, I already had contact with the beamline scientist and he provided me with some scripts. So, thank you.
Okay, we take a few minutes for a break, just waiting for the different people to come back. So I made so the tutorial this afternoon will be based on Jupyter Hub, especially. So the file that contains everything we need is registered here. So github.com/. SELEX kit, and I'll show you how to go there. So github.com/SELEX kit, and then go to SELEX training and PiFi. And the file we're interested in is ssx.ipnb. And what you can do is to do directly a download here and save this. So save page as ssx.ipnb. And then you can open this directly with Jupyter Lab. I don't know if you have Jupyter Lab installed on your computer. So are you familiar with the Jupyter notebook or the Jupyter Lab interface? It's okay. So, well, this tutorial will show you some ideas on how to use PiFi with Jupyter Lab. So here I'm using the lab interface. We'll focus on 3 topics. Maybe I'll put it larger. I don't know. The first one is diffraction imaging from raster scans, especially when it comes to crystalline material, in the sense of materials composed of large crystallites. Then we'll discuss about lossy compression for single crystal data with application to rotational macromolecular crystallography. And we'll discuss a bit about synchrotron serial crystallography, the pre-processing that we are considering to do on ID29, the beamline, which will be specialized in serial crystallography. The tutorial uses the latest features of PiFi, so the version 0.21, which came out last week. And this was designed really to run on GPU using OpenCL. So the code runs on any GPU, regardless if it's an AMD GPU or an NVIDIA GPU. It runs also on Intel integrated chips. Yeah, for now it's a strong pull request. Some things are working on pure CPU, but because we had a very strong speed constraint for ID29, we've developed directly the code to be targeting GPUs. Everything related to macromolecular crystallography, we've used 2 external tools, which are XDS. So this is a piece of code to perform the reduction of single crystal data, mainly focusing on proteins, and Crystfel, which is a well-known tool for analyzing serial crystallography data. I'm neither a guru in XDS, neither a guru in Xfel, so maybe I made some stupid errors, and I count on you to spot them, because well, maybe I'm doing a complete misuse of those tools, but I've tried to use them to validate everything we did in this tutorial. So the layout of the tutorial is yeah, first Jupyter Lab, then azimuthal averaging, and we'll start to discuss a bit about distribution of pixel within rings and things like that. We'll perform a sigma clipping step by step. Then we'll focus on the sparsification of diffraction data with the presentation of the ID29 beamline. We'll try to validate the sparsification on rotational data with XDS. And we'll finish with peak finding with a comparison with the PiFi 8 from Cheetah. We'll perform a comparison with what is implemented in PiFi and try to validate some performances. So let me restart the kernel. So concerning the integration of Matplotlib, I'm using the widget interface. This means that we need the package IPMPL in addition to be able to use Matplotlib. Here we are importing everything we need. And what is important is that we have a PiFi version 0.21 because many things are likely not to be working if we use something else. Were you able to retrieve the notebook? Are you trying to execute it at the same time? Okay. If you have any problems, just tell me. So the first thing we'll do is just retrieve one image, and I picked the image Pilatus 6M, which comes from a data set that Dectris was using to advertise for the Pilatus detector. So it's an image, I think it's an insulin data set, but it's what matters is that it's an MX experiment. So I'm using Fabio to read the data. And previously I did from PiFi GUI import Jupyter. So when we use Jupyter here, it's the interface from PiFi to Jupyter, and we'll just display the data. So this is the one frame taken out of the diffraction data, so we can resize the image. What do we see? Well, first and foremost, we see that it's a Pilatus detector, so it's made of several modules. So here we have 5 times, about 12 modules vertically and 5 horizontally. So each module is 100 kilopixel. We see some background scattering that could come either from some grace or an ice ring, but I would say rather some amorphous compound, so grace. And well, we see here a beam stop shadow. And if we zoom in, if we zoom in, we see little spots like this. Those are our Bragg spots. And here we have probably a hot pixel, and here we have Bragg spots. And yeah, that's what we are interested in. So this is a typical image, the kind we'd like to treat. Yeah, so first of all, well, coming from, it's a tutorial on PiFi. We'll perform the azimuthal integration of this data. So what we do is we use PiFi.load that is able to load a geometry, and we use Pilatus6m.pony, which correspond to the geometry of the associated file, and then we just print the file. So we have a Pilatus6m with the pixel size corresponding. The wavelength is here, and the geometry has been built without any calibration, I guess, with just the beam center given here, probably extracted from some headers. Detector distance is 30 centimeters, and yeah. So the geometry in the sense of PiFi is written on one line, and for convenience we provide the fit2d equivalent. So sometimes it's easier to read the fit2d equivalent, but yeah, this one is the one that is used to perform the calculation, and the second line is a transformation that is done. So the Pilatus 6M is fairly large. The beam center is pretty much in the center, and yeah, we defined that we'll work on 1,000 beams. This is a bit arbitrary, but having too many azimuthal beams will make the calculation slower. Having too few may be an issue when we want to model the shape of this this amorphous ring. For Pilatus detector, we say that anything that has negative intensity will be masked, so we update the mask here. We will use a Cyton integrator. CSR is using a sparse matrix integrator, and here is the way to perform the azimuthal integration. So for 1D integration, we use a Poissonian error model. So the Poisson law says that the uncertainty, the variance of the variance of a distribution is equal to the mean value, which translate more or less by saying that the uncertainty on the value of a pixel is the square root of its value. And then we plot the result. So it gives us something like this. So we see here a background with an amorphous bump here that we were seeing previously, and another one around 30 inverse nanometer. And on top of this, we have spikes which correspond to Bragg peaks. On the 2D integration images, we see the structure of the detector with those waves. We see here the main amorphous contribution to the background, and we see the small Bragg peaks here and there. And the whole idea is basically, can we model this nice background and separate this background from the Bragg peaks on top of it? That's the core idea of this tutorial. So let's consider this amorphous bump. Hi, Gudrun. So we have this amorphous bump, which is around 17 inverse nanometer, and around 30 we have almost, well, we have very limited contribution to the background. So can we have a look at the pixel contributing here at 17, so here, and pixel contributing at 30? What does those pixels look like? So here I put a list of targets, and I do the histogram. So I'm using the sparse matrix that has been defined here. I'm extracting the pixel coordinates I'm interested in. I'm calculating the histogram of it, and then I'm fitting a Gaussian on top of it. And this gives us something like this. So at Q equals 17 inverse nanometer, we have this bump centered around 18 or 19 counts. So this is the value of the pixel. And if we consider the other one at 30, the other ring at 30 inverse nanometer, we have also bell-shaped curve, bell-shaped distribution that is centered around 7 or 8. And then this is why I fitted a Gaussian on top of it, and we have here the center of the Gaussian that has been fitted, so 17 and 6, and the full width at half maximum. No, sorry, not the full width at half maximum. The standard deviation of the Gaussian, which is a 4 and 2. So here we have sigma equal 4, and here we have 2. So yeah, that's the value, the plot. But if we look at one of the actual histogram, we see here we have the intensities, so 52 and so on. So the maximum is sorry here at 6, and then it drops to 0 more or less, and it's almost 0 for a lot of time, and we have still 1 pixel that counts 84. So in this blue, in this green distribution, we have 1 pixel that is very much here to the right that counts for 1. So this is clearly an outlier, and this one is likely also an outlier, and this one as well. And yeah, well, let's say anything above this, those are all outliers, or maybe even from here. All those pixels are probably outliers. And those pixels are probably Bragg peaks. There are some contribution from a Bragg peak. It would be really cool if we could have a way to say, okay, this is background, and the pixels that are here at the right, those are Bragg peaks, and let's try to separate them. And the whole tutorial is around this. Where can we set the limit, and how can we have this distribution to represent the background, and have on one side the amorphous content, and on the other the Bragg contribution. So yeah, is you get the idea? It's okay. So one of the core ideas is to consider those bell-shaped distribution, so the green and the blue one. Let's say this is close to a normal distribution, which can be modeled as a Gaussian curve. And yeah, sorry. And if this is true, we can say, okay, here is the Gaussian curve. We have it centered around the mean value. If we consider all pixels above the mean plus 1 standard deviation, this is 16%. Above 2 standard deviation, this is 2%. And above 3 standard deviation, this is 0.1%. So one of the core idea is what we have information, let's say above 2 or 3 sigma. This is only outlier data and probably Bragg peaks, maybe something interesting in looking at. And what is below, let's say it's just some background noise, and just model it with the mean value and the standard deviation. Yeah. One small warning, there's well, we use sigma and the standard deviation for two things that are slightly different. The first one is the actual standard deviation, which corresponds to the uncertainty about 1 pixel value. And this is what we're interested in, especially in this tutorial. And there's another one, which is the uncertainty about the mean value And this one is the standard deviation divided by the square root of the number of pixels contributing. And this is what usually PiFi reports, because most of the time people are interested in the uncertainty on the reported mean value that I am giving, and not at they are no more interested into the pixel anymore. So we cannot just use the standard deviation as coming out of PiFi directly because of this difference. So there's two ways of getting the uncertainties. The first one is the one we've used, is to say, okay, the detector follows Poisson law. For example, it's a Pilatus or Niger detector. Those are photon counting detectors. The variance is equal to the average intensity. If I want to be precise, it should be the yeah. So the variance is equal to the average intensity, or in the case of many detectors, we could say that the variance is equal to the average intensity plus some readout noise. If we assume that we have mostly amorphous data, we could assume that there are no outliers in the ring, and we could calculate the variance as being the difference to the mean squared and averaged out. So as we would do in a distribution where we have no clue of what law it's following. And the next cell gives you a way to show them. In the case of, so well, the way the uncertainty is calculated is not having any effect on the average signal, but it has an incidence on the standard deviation. And if we zoom in, maybe I'll cannot zoom out anymore. Yeah. So here in blue, we have the curve obtained from the Poisson formula, and in orange, the one obtained from the azimuthal deviation. So azimuthal deviation has much higher noise, let's say, or standard deviation compared to the Poisson one. So now the idea is, can we use this information basically to get rid of all those peaks and keep only a smooth background here? So this algorithm is called sigma clipping. It consists in iteratively rejecting outliers from an ensemble based on their values and the mean and standard deviation of the ensemble. And then we reevaluate the mean, the standard deviation, and we reject some further outliers. So the core parameters of this algorithm is the number of cycles in the iteration. And usually 3 to 5 cycles is pretty good, but theoretically we should go on until nothing changes anymore. And we have another important parameter, which is a cutoff. The cutoff is at when do we consider a pixel is an outlier. So it's the intensity of this pixel minus the mean. If it's greater than n times the standard deviation. So if we want search for Well, there's a new version of SciPy that just came out, but apparently the documentation is not yet up to date. But yeah, basically, it's directly inspired from the SciPy stat sigma clip. And the parameters you will find are roughly the same. So it's an iterative algorithm. Apparently the version in SciPy continues until nothing changes anymore. But in the version implemented in PiFi, we have a limited number of cycles that we can do. So okay, so let's do just one cycle. So we just remove the outliers and we recalculate the distribution. We cut at a signal or noise ratio of 3. We perform one cycle and we redisplay the previous curves. And what do we observe? Basically, most of the peaks have disappeared. This is a first interesting thing. Then there's another feature that is interesting or not. The fact that some bins became completely empty, and this is a bit of a problem. And this occurs mainly with the Poisson distribution. So the fact that peaks have disappeared is a feature we are looking for. The fact that we have some bins getting empty and having at the end 0 values is something we are definitely not looking forward. So to remove this effect, what we did initially was to reduce the number of bins that we have so that there are more pixels in it and that the distribution is better calculated. But it didn't turn out to work very well. So basically we switched from using the Poisson distribution to an azimuthal deviation. The drawback is that the variance with the azimuthal distribution remains much higher. So we need to perform more cycles, but it converges to the same value after a certain number of cycles. So it's an interesting thing to see. The other option that was possible was actually to increase this signal over noise ratio. For example, if we remove pixel only that have a signal over noise ratio of 5, the number of holes that we are observing is less. But then we need to do much more cycles. So with 10, we still have a hole here. So there's something definitely wrong. This is why basically we implemented this azimuthal deviation stuff. And well, we'd like to be able to tune this parameter, signal over noise ratio, automatically. Let's assume that if we have something that fits already a Gaussian distribution, a normal distribution, we'd like to discard at maximum 1 pixel. And if we do that, depending on the size of the distribution, so the number of pixels falling into a Q-bin, this formula gives us the limit signal over noise ratio, so that we discard at maximum 1 pixel. And well, it turns out to be fairly robust. It gives the signal over noise ratio, which, for example, I can. So if I take the square root of 2 times if I have 1,000 points in my distribution, so it gives me a cutoff at 3.4. If I have only 10 pixels in my distribution, the cutoff is at 1.6. And if I have 10,000, my cutoff is at 4. So let's say it's a convenient way to adjust the signal over noise ratio to automatically remove pixels that I don't want, and to remove as few pixels as reasonably possible. Okay, so let's perform a complete sigma clipping and have a look. How many cycles am I performing here? It's the default value. So yeah. So here in blue you have the azimuthal integration, and in orange the sigma clipped, and it really gives a nice approximation of the background, and you see every single Bragg peak coming out of it. And this algorithm is really the core of everything we'll do later on today. Are you convinced with this? Do you have any question? Okay, basically the parameter for sigma clipping are the number of iteration. Well, we usually use 3 to 5, but yeah, after 3 iteration usually it's already converged, and the cutoff can be automatically adjusted using Chauvenet criterion. And yeah, there are 2 ways of calculating the deviation, either from the Poisson statistics or for the deviation to the mean. And the latter has been developed for non-Poissonian detector, especially the Jungfrau detector. There's a typo. Especially the Jungfrau detector developed at PSI, because it's an integrating detector. Yeah, let's speak a bit about performances, because yeah, performing an azimuthal integration can be done in less than a millisecond. But here we are speaking of performing 3, 5 azimuthal integration, maybe 10 azimuthal integration. So yeah, the code needs to be ported to GPU. So let's check how fast it is. So here I'm performing the same integration using either pure Python or using a version that is ported to the GPU. The computer on which I'm running currently has 3 GPUs, and the fastest one is an AMD GPU, which behaves really in a really strange manner, because when I use timeit, the performances it returns is really bad. And I don't understand. For example, if I do much more than just sigma clipping, I had previously 12 milliseconds, and here it's, yeah. I don't know why, but the reported performances on this GPU is really bad. This GPU is an AMD Vega 56, so 4 or 5 years old, but yeah, the performances when it's in benchmarking mode is pretty bad, especially compared to what it can do when it's not in benchmarking mode. So yeah.
But it's written in your output that 10 loops you did for GPU, while 1 loop for CPU, right? Or
yes, but this is automatically corrected. For example, let's imagine I'll do a new cell. let's say 1 is true. That's something completely stupid, but maybe I want to benchmark it. This will take quite a big number of iterations, and it will perform the same stuff over 7 seconds, and it will perform how many million? 100 million times the calculation to be able to measure that one execution takes 13 nanoseconds. So the figures that are given here are already corrected for the number of loops executed.
Okay, thank you.
Yes, on at work, because now I'm remote working, but at work I have an Quadro A5000, and the speed up that I observe is not a factor 2, but it's a factor 24. So yeah, it depends a lot on the GPU. But what matters here is that we have a GPU that is able to perform the calculation. By the way, did you try to run the calculation on GPU? Do you manage? For those who are trying to execute, does it run? Sorry. So the first thing we'll try to do is to, well, this gave me the idea of sparsifying the data for ID29. We have the problem that the detector from ID29 will operate at 1 or 2 gigahertz, and we have a maximum write speed to the drive, which is 2 gigabytes per second. Roughly, this means that we need a compression ratio of the order of 10 times. So we have 3 main options. Either we run 10 times slower, option 1. Either we save 1 frame out of 10, option 2. Either we save 1 pixel out of 10, option 3. And the idea here is to go for the option 3, which is saying which pixels are worth saving, which pixels are likely to be Bragg pics, and which pixels are likely to be background. So the next cell, well, we retrieve the integration method that we were using previously. I can print what it is. This allows us to retrieve from within PiFi. We have a dictionary with all the engines that are available. So I can yeah. So the engine that was initially used was without pixel splitting, CSR implemented in Python, and we see here that we have 1, 2, 3 azimuthal integration engines. Yeah, maybe this explains why. This explains why it's slower, because here we are using a very low-end GPU, and we are not using the one. It's already better than previously. Not very reproducible as a result. Yeah, well, my idea was to use this GPU. So yeah, the idea is that we have an OpenCL compute engine, which I call PickFinder, which is able to perform the sigma clipping and to perform the sigma clipping and then report all the pixels that are considered as positive outliers to the distribution. I'm trying to fix this. Well, it doesn't want. Well, we'll use the slow GPU. I'm sorry. Hmm. Sorry, the bug is here. Well, no, it doesn't run faster. Okay, but forget about this. What is important is that if I take the previous image, I found with well, just the default parameters. I found, let's say, 16,000 pixels worth to be saved, which are basically positive outliers. And if I want to perform the profiling, yeah, the figures are completely nuts. So apparently it takes 80 milliseconds, but if I switch back to the documentation, On the very same computer, it was 10 milliseconds. That's something I don't understand. Okay, let's assume it's proportional. So we see that we needed about 2 milliseconds to send one image. So it's a 6 megapixel from the CPU memory to the GPU memory. We transform the data to float 32. We perform this basic correction. So the figures are pretty high. And then for the sigma clipping, it takes 60 milliseconds and an extra 9 milliseconds for the peak search. And the retrieval of the data is almost instantaneous. So that's the idea. We send the data to the GPU, we perform the sigma clipping, and we look at positive outliers that we retrieve. And in this cell, we overlay the pixels. So it's the same image as previously. And everything that is, let's say, darker corresponds to pixels that are not saved. And here we see which pixel we are likely to save. Well, we are considering to save. So in some part of the image, there are more. But we can see that Bragg peaks, are usually well spotted. So here we have a series, and we see that they are well picked. Yes, Alexander.
So several questions, sorry. You process this image for 80 milliseconds, so basically you can process like 12 images per second from 2000. So it doesn't help you to basically transfer data.
Well, the figures that you are seeing here, those are on my computer. The code was designed to run on an NVIDIA Tesla V100, which is pretty different from the GPU I have on my computer at home. So I'm making the demo on my computer at home. I could have made it on the computer at ESRF, but well, my colleagues had problems with connection this morning, so I considered it was safer to perform the demonstration at home. But
yeah, that's fine. What are the numbers at work? So what are the best numbers? What is the speed of processing per image?
Less than 4 milliseconds.
But then again, it doesn't help you. 4 milliseconds meaning 500 hertz, not 2 kilohertz.
Yes, but we can have several engines like this into one computer, and we have several GPUs into one computer.
Then
and we have
yeah, I understood. Yes, thanks. You explained it. So just more computing power. But more interesting problem is that in this way you're saving only like positive outliers. But everyone, like every crystallographer, knows that there are Bragg peaks which you cannot see, cannot detect, but adding up multiple patterns, that's what serial crystallography does. You're getting higher resolution. So by saving like this, you're just discarding resolution to everything what you can see. That's it. We were testing this like, I don't know, 5-7 years ago, and then you just cut your resolution to what you can see.
That's true. You're limited at if you cut at 2 sigma, you're limited at 2 sigma.
Yeah. Okay. Well, it's fine if there is no other way. It's fine. It's just something that
well, the alternative is running 10 times slower, or the other alternative is
buying more computers and faster transfer.
No,
nodes.
Buying more computers will not allow us to go faster. The problem is that the storage system is not able to cope with more than 2 gigabytes per beamline.
Yeah, well, it should be just upgraded, because like at the European XFL, it's like 40 gigabytes per second is fine. So it is possible. It just costs money, basically. Well, yeah, I'm not saying that it has to be done. I just trying to understand.
I think you spotted it right. It costs money.
Yeah, okay, thank you very much. You at least explain me the solution you have chosen.
Yeah. For now, the solution has been implemented. It has been tested to work. We are at the very beginning of the commissioning of the detector on the beamline. It has been installed just a week or two ago. So yeah.
Actually, by the way, talking about this, you're talking about Jungfrau, right? Detector.
Yeah, I'll introduce it just a bit later on.
Mm-hmm. So basically, you process every like a half megapixel image separately here, or do you merge first, because Jungfrau has separate output for data from each module? So do you first merge them together, or do you process every?
First, we perform the image reconstruction.
But this also takes time, right?
Yes, but it's done on a different part of the computer.
Mm-hmm.
So the computer is built up of different parts. Mm-hmm. Having all this computation offloaded to the GPU frees CPU resources to perform the image reconstruction, the frame reconstruction, to be precise. And then frames are grouped in larger chunks in order to perform the pedestal correction also on the GPU. So those larger chunks are sent to the GPU. The computer we are using is an IBM Power 9 server, which has a very large bandwidth between the CPU and the GPU. About twice the fastest that can be done today with PCI Express 4. So it uses some dedicated link to transfer the data to the GPU, and from there we are able theoretically to process data at 1000 frames per second on 2 GPUs. Because here, yes.
Sorry, it's not just actually dark subtraction, it's also like gain multiplication, right? It's Jungfrau,
yes,
with 3
absolutely.
gains. Okay, but
when I say pedestal correction, it's the complete pedestal correction with the 3 gains and so on and so forth.
Did you estimate how much all this processing, like image assembly plus all those corrections, take?
I did some benchmark initially on the pedestal correction for the GPU, and we arrived exactly to the same conclusion as Philip from PSI. I guess you know him, which states basically that we need chunks that are large enough so that the reading of the pedestal values, so the pedestal and gain values from the central memory, is neglectable compared to the number of frames we are processing.
And by the way, do you work with HDF5 files, or is this raw native format of Jungfrau?
Well, the guys who are doing the interconnect between the detector and who will manage the saving are working directly with the PSI API, and they are retrieving the raw buffers. And so they are not reading HDF5 files. They are receiving directly buffers in UDP. I don't know exactly all the details, but then they take the buffers from the different modules. They assemble them into 4 megapixel images, and those 4 megapixel images, so with before pedestal correction, so uint 16, are sent to the GPU where they are pedestal corrected, and then sigma clipped, and yeah.
It would it would be really interesting to see the whole pipeline. How long does it, or how many images per second you can do with these corrections? Well, all together.
That's something we will start working on soon, because we didn't have it yet. Everything is assembled only for less than 1 week now. and I got the feedback that from the guy who are doing the integration that it's working. That's
Thank you very much.
a
Yeah,
very
thanks.
positive feedback from them. So yeah, I honestly expected to have more trouble, but I don't know yet the figures that we obtained. So yeah, presentation of the beamline. So that was actually just after that. So ID29, it's a beamline dedicated for synchrotron serial crystallography. Well, there are 2 experimental hutches. The first one will be used, and we'll use either some jets to deliver crystals, or more likely some membranes with raster scanning. Well, here, that's the ESRF source. We'll have a chopper that will initially operate at 1 or 1.1 kilohertz, and the idea is to have the data processing, the data reduction performed at this speed. So the detector is Jungfrau 4M, which comes directly from PSI. And yeah, the idea is so we have 8 modules. Each of those 8 modules are connected with one 10 gigabit link upstream that it will they will fill if operated at 1 kilohertz. Those 8 links will be multiplexed into a 100 gigabit link and connected to one port of a Power 9 computer. And then there's over there's one process receiving the data that will split the different modules, flip the half modules, and assemble the different frames into 4 megapixel images that will then be sent to the GPU, be sparsified over there, and only the background, the standard deviation, and the pixel containing Bragg spots will be retrieved and saved. But of course, it's still possible to save the 16 megapixel, no, sorry, the 4 megapixel image row before the in 16-bit integers, if operated either at full speed for 30 seconds or at reduced speed for a longer amount of time. And for operating at full speed, we are limited by the amount of memory of the computer. For now, the computer have half a terabyte of RAM, but it could be increased to 2 terabytes of data if needed. So that's for the Jungfrau 4M that we are all doing this work. So as I said, we can operate at lower speed. We could use a kind of veto algorithm. I think that's the solution that was chosen at EXFELS. That means you keep only the data that you consider have some signal in it, or you keep them all.
Unfortunately, XFEL just wants to use veto signal. They never implemented it, so they're still saving even empty frames. But yeah, hopefully at some stage it's going to be used. You're right.
So yeah, well, basically this is where Nicola comes into the game, because he said that he'd prefer to have something that looks like a veto algorithm, but we'll let him present what are his ideas very soon.
Actually, may I ask one more question about this implementation? So didn't you try to consider like NVMe for storage, or for intermediate storage instead of RAM? For single module, it should be fast enough.
We don't have one computer per.
Okay. So you're using one.
We have one computer for all 8 modules.
Okay.
And the NVMe drive is not even fast enough. We have.
Right. No, for all, you're completely right. That's actually what they did at the European Expo, and for most of the new detectors, it's just single computer per module, and then you are fine with the data rate.
Yeah.
Okay, yes, thank you.
So to evaluate what we can do, I took a series of 1000 frame with an Eiger for M. So with the geometry, the mask, we used 1000 azimuthal bins. This is something that has been already tuned for the Jungfrau, and the sweep point. So if we want to reduce the number of azimuthal bin is around between 720 and 750. We choose an azimuthal error model, and yeah, we picked all pixels above 2 sigma. We already know that for ID 29, we will probably operate at between 1.5 and 1.7 sigma. So in order to save as much pixel as possible. The polarization factor is something that is really important. We have a polarization which is well known at synchrotron, and we need to correct for it. So basically, the program that does this looks like that. This here is the complete command line. Oops, sorry. So if I go to I'll just rename the file name as live. Yeah. So here it picked the proper GPU, let's say, the AMD GPU, and we see here that it's saving about 130,000 pixels per 4 megapixel. So right now it's reading the data and performing the sparsification. So the frames per second that are printed here are not decoupled from the read speed from the data. But yeah. So if we look at the data, the one that we have just created, this one. So here we have the background, which has been calculated. And if we zoom in, we see the error bars that were recorded. So here we have so this is the image of the sorry, where is radius at the end? What is it doing here? Okay, so here is the value of the radial position. Pixel with nans are actually masked pixels. And here we have the where each frame starts and the coordinates of the within index and intensity. But if I show you this, it's a very large array, and it contains the raw intensity. I should have done it this way. Well, so here, yeah, we have the values for the different pixel. So here we have pixels which have been gathered, which have intensity of 9, 12, 14, 10, here as low as 6. That's just to give some example. And here are the raw values for the pixel, and the index of those pixels are saved in this array, but it doesn't make sense to transfer it because yep. So as I said, the compression speed was measured between 500 and 1000 frames per second when we were treating data from memory. Those data can be densified using an extra program, which is multi-threaded, but not shipped as part of PiFi, but as part of Fabio, because Fabio is easier to install than PiFi. And so we have a software package that redensifies the code. Just yeah, it's multi-threaded, as you can see. And it's operating at about 100 frames per second. It's not as fast as but it does not use any GPU or any other fancy stuff. It's just a simple multi-threading. Yeah. We see that writing the data actually to the disk took much longer, about almost twice compared to the speed for decompressing the data. And here we can see that the size of the dense data compared to the size of the sparse data. So we have a compression ratio of 6.5. So it's close to what we are looking for. Yes, Alexander?
Actually, question to the compression ratio. If you save only those like high value pixels, why the compression ratio is so small? I would expect higher compression.
Yes. Well, you have to consider that the data here are compressed with bit shuffle LZ4, and they contain mainly lots of zero, which makes them not very well. That makes them easy to compress. The data which are stored here inside are also compressed in bit shuffle LZ4, but because they contain mainly floating point values, they don't compress as well. So this reduces the compression rate that is visible as disk space.
Why don't you just make integers from floating point? Because it's like leftovers of photons doesn't really matter.
Not with this won't work with Eiger data. We're not working with kilo electron volts. We are working with photons already.
You mean Jungfrau, no? Yeah, Jérôme?
No,
Well,
but the data we are using here are Eiger data.
Right, but again, everyone is interested in something what is like single photon counting, basically. Half photon is not really interesting to users, right? So you can truncate. Well, users will require everything, right? If you
On
ask
the
them.
one hand, you said that you're interested in the noise, and on the other, you said you don't.
Well, I'm a user. I know that if you ask users, they will say you need everything. So yeah, but there should be some compromises, and compromise at the level of single photon, I think, is well justified. So all our tests show that it's fine to truncate to single photon values at least. So yeah, thank you. But and actually 2 more questions. To process this data, you have to uncompress it, right? So basically,
for now, you're perfectly right. That means in order to be able to validate the complete chain, we have a compressor and a decompressor, and we even regenerate some noise on the data to have something that looks like the noise you would have. So we are injecting a lot of random number values in there in order to have a software like XDS to accept those data. Because if the data were clean without any noise, XDS will just complain and say that those data is garbage, because there's not the noise doesn't look like what it's expecting. So we are regenerating the noise so that XDS agrees to process the data.
can you make some H5 plugin for basically uncompressing on the fly?
It's not excluded, but it's not on the to-do list. It does not have a high priority for now.
And last question to this part. So geometry of Jungfrau detector, how did you make this one?
Sorry?
Geometry of Jungfrau. You have these 8 panels and you need to know where they are. And from image at the website, it looks like there's either Z offset or inclination. So how do you make geometry?
For the geometry itself, first of all, we did not yet characterize it precisely. So we have pixel located, let's say, within 75 micron. So we have just a rough approximation of where the pixels are. And then we need, of course, to characterize them. I've performed the calibration of all Eiger detectors that have been delivered 2 years back at ESRF, and we have the procedure with a grid of holes. Mm-hmm. And well, I've characterized. We received the 3 or 4 Eiger 4M, and yeah, the procedure are ready. It's not yet done for the Jungfrau, but it's something we'll have to do, and yeah.
Yeah, but that's perfectly fine. It's just be careful, because what I've observed, Jungfrau detector have Z offset of panels, which is of the order of like hundreds of microns, which is quite important already for this size.
It's huge. This sounds huge.
Well, so just with your mask, it might be possible to locate the Z offset. So yeah, just take this into account.
Yeah, that's something that was not foreseen, but
yeah, well, we also didn't expect it. I just measured, and yeah, it happens. That's real life. Sorry. Thank you very much.
Well, it's not with the people doing AMIX that have most concern about this module positioning in space. It's more people who are doing powder diffraction and PDF, where they want to go to very, very high Q. And yeah, usually they are extremely cautious about that. So it's not the same group of people, but I'm the only interlocutor for them. So yeah, I can transfer the know-how from one part to the other.
But still, I mean, 100 micron from one panel, this will mess up the position of the expected Bragg spot with the measured Bragg spot. So even for us, it's going to matter at some point, Jerome, I think. So that's something we will have to do.
XDS has the nice ability of retrieving the distortion map that this is why we want to
XDS does. I'm not sure Crystal does so good.
Crystal doesn't. Crystal
Yeah,
doesn't.
so
You have to do it manually.
you
So
have a key offset per panel in Crystal that we will have to be to know ahead, I guess, or to refine at some point. But 100 micron gap at starting is quite important. So if we can know it beforehand, that would be great, I guess. Thanks, Alexander.
actually, maybe you can even take the distortion map from XDS and try to convert it into Crystal. So I never tried, but it might be possible.
Yeah,
the problem is that XDS does the mixing of the parallax effect and the distortion. And well, my idea would be first to play with some Eiger with CDT sensors where we know that we have little parallax effect to validate the procedure before going back to silicon sensor like the one we have on the Jungfrau. If you trust me enough, I'll just perform the XDS data reduction for a data set that was again provided by Dectris. So it's some data that were collected at PSI, and I made the integration with XDS of the raw data. And the same one with Poisson noise, for example, and we can see, well, okay. Well, the until 2, well, I over sigma, where is I over sigma until here, which correspond to 2 angstrom resolution limit, we have roughly the same result. Of course, any crystallographer would say that the last bit of the last stuff is the most important for him. But, well, maybe this would make the data collection possible. Well, the completeness of the data remains the same. And the R measured as well as the CC1/2 look similar. And Nicola did some further investigation on the reconstructed volume, or the reconstructed electronic density. Maybe you can comment a bit on this, Nicola.
Yeah, I'm sorry, I don't have the images right there, but looking at FOFO maps, for example, that was the signal was still there. Of course, the idea now is to reproduce that with still images, and that's what we're going to do. And of course, what we have in our hands, we have, I mean, not from Jungfrau, but still this data from Eiger, that's data which can be phased. So I think that would be, if we can show that with a minimal number of images which can be phased, and we go through this classification, re-identification, and we can still phase, I think that would be a nice validation of the procedure. So that's what needs to be done next with our test data. But with oscillation data, what we had in our hands was some oscillation data and FOFO maps, and this was we could still get the same features with not the exact same level, but reasonable identical levels. But of course, because ID29 will be SSX beam9s, we have to go through the crystal processing, which is different from XDS, which is processing differently. So we have to make sure this is also procedure that could be used.
So, well, all those files are available if you want to investigate into them. So as I said, I'm not a guru of XDS, but it apparently validates the fact that we have kept enough signal to be able to reprocess them. Well, from this, Nicola had an extra idea. Was basically he wanted to have basically what PickFinder 8 was doing and to have it running in real time. So PickFinder 8 is an algorithm that is implemented into Cheetah, which is a software for treating serial crystallography data. It's implemented in C++. And well, it's named PickFinder 8 because it goes with 8 subsequent steps. Basically, the two first steps are the sigma clipping, and then it considers some patch around a region to calculate the number of connected pixels, and then calculates basically the center of mass of a pix, and there's a step for excluding neighboring pix. This is something we didn't re-implement, and yeah, because we had the first step already implemented into PiFi, the idea was, can we reproduce the behavior of PickFinder 8, and how does it behaves compared to PickFinder 8, because apparently this was the reference algorithm. So the reference is already pretty old. Maybe better algorithm came into the game since that. So maybe what I'm presenting is already obsolete. But yeah, I used some Cython wrapper for PickFinder 8 that is being installed here, compiled, and so on. I had to create some compatibility level here, and basically PickFinder 8 on one image, we are still playing with our Pilatus 6M image. Well, it takes 140 milliseconds to run on one image, and just checking that I'm getting 189 Bragg pics on the image, and here I'm displaying the stuff, and looks like Bragg spots. I'm not sure to use properly the piece of software, but apparently it reports me where the Bragg spots are, and maybe that's the most important. What is funny here, we have a line, but it didn't spot this one, but the other one are properly spotted. But yeah, there are some, I know this is a hot pixel, this one as well. Yeah, well, so the Nicola was suggesting to go into this direction, because if we want to re-implement the Bragg, the Veto algorithm, we should have some metrics like the number of Bragg pics we have on an image. And yeah, so this is what we implemented. So we perform the sigma clipping as previously. We consider a patch, a small patch, 3x3 or 5x5 pixel. Is the pixel of interest the maximum of its patch? Are there enough connected pixels in the patch? If so, we report the centroid, we integrate the intensity, and we perform the error propagation accordingly. And yeah, so what we had previously was 16,000 or 17,000 pixels, and after going further on, we have 340 Bragg pics remaining, it's a bit higher than what we had for PickFinder 8, and yeah, the values for the number of cycles here is slightly different. Here we have only 240. The patch size is larger, but yeah. Okay, let's overlay the two images, and yeah. So in orange we have the original implementation from Cheetah, and in blue we have the one from PiFi, and we see here that we have some very weak Bragg peaks, and those were not spotted by PickFinder 8. If you look at this series, there's a series here, and this one was not spotted by the version from Cheetah. So I don't claim that the version I've made was better, because I don't know how to use the version from Cheetah, but I'm pretty happy with the result I got, and I was honestly surprised to obtain better results. But yeah, it's, let's say, something that works. So just before rerunning it, here it takes 11 milliseconds per image, so it's almost a factor 10 faster, and yeah, most of the time is actually spent in the Sigma clipping. The pick finder itself doesn't take much longer than just extracting the peak position. I will run it again, but the performances will degrade. I don't know why. And it was run on the same computer. That's really surprising, but well. So what I've tried to do is basically to extract the peaks for the serial crystallography dataset. So here is the command line. And sorry, I have to copy from the keyboard. So geometry, mask, polarization. So I've kept peaks above 3 sigma, while for the sparsification I'm cutting at much lower values. So the R model, I took the azimuthal. I've added some extra noise that could be done for the readout noise. I want a patch 5x5 with 3 pixels connected into it, and I like to report some profiling. Why reporting some profiling? So that you can see that the same GPU is giving different speeds, very different speeds from when running to Jupyter Lab or not. So we have again the number of peaks that are of peaks that are reported.
It's actually the number of peaks, right? Not the number of pixels.
Yeah, it's the number of peaks. And yeah, here you see that the sigma clipping takes the median value is less than 9 milliseconds. The peak finder is 2 milliseconds. Here it's reported 10. So I don't know why does this factor 5 a difference in speed. And the copy of the image, copy raw image, is here. 1 millisecond. Well, not that big difference for the copy, but still. And if we look at the image, so here we have the number of Bragg peaks per image. So it goes from just a few. Here we are at 50 to 600, and we could imagine building a veto algorithm on this to be able to select the frames that we'd like to keep and then keep all the data. So what is Nicolas, you have
Yeah,
a
no,
comment?
sorry, just the idea is because we're so close to, you're doing all this processing on the image while they are still in memory, that if we can already find the Bragg peak position, the idea is to feed that then directly to Crystal for the next stage. So we should be, the idea is to perform hit finding and peak finding while the image are still in memory. And if we can store then this information for Crystal, that's already a good point. And we might also be a little bit more maybe relaxed at this stage. Depends if we think about this veto idea or not. For now, we don't know, and we are going to keep all the images. But the idea is then in Crystal, you can also put a bit more restraints on the peaks which have been found, if it's in this CXI format, like the minimum number of pixels or minimal signal to noise ratio. And then if you don't have to go from scratch and perform peak finding, but you can just narrow down maybe the number of black spots which have been found at this first stage while the images were still in memory. So that's the idea, then to see how it can be properly implemented.
So yeah, the speed is slightly slower than what we have for the sparsification. So you see that we export as previously. So here we have the frame pointer, and here we have all the data. So we have the index of the highest intensity peak. We have, of course, we have performed the background subtraction for all of them. We have the intensity for the peak. So this is the intensity of the different peaks. We have the associated position in Y, in X, the uncertainty, the propagated uncertainty. And yeah, so just to finish, I've tried to use this algorithm to extract the peak positions, and I've reduced the data set with Crystal using the native peak finder 8 as available from Cheetah. And beside this, I've tried to inject the coordinate of the Bragg peaks that we found with this implementation. Well, for this, for sure, I won't do a demo in live, but if we go to this one, okay. Just I'm a complete newbie with Crystal, but what I can do a grep for cell parameters in the output. So those are all the cells that were found by Crystal. And I can just count. So Crystal tells me, well, the default one, which is used in the tutorial, that 500 and 57 out of 1,000 frames were containing some crystals, which looks pretty good. But if we are looking for the parameters which start with 3.8,
That's the tetragonal lysozyme.
yeah, because
Yeah,
well, Nicola did the experiment, and apparently it's lysozyme that was used. It found one tetragonal lysozyme out of the 1,000. So with the version where we have replaced the original PickFinder 8 by a tweaked version, so I had to create by hand this mix.h5 that is a mixture of the raw data that looks like this. So if we look here, sometimes we have some nice Bragg peaks, and I've injected next to it so the number of peaks and the intensity, as well as the x and y position for the different frames. So this is something that I've created manually before being able to run Crystfel on it. And now if we just grep for cell parameters, the result is a bit disappointing because we found only 188 crystals. So it's less than with the original version. But if we search for something that would contain a cell which starts with 3.8, actually we found many of them. So some of them are wrong. Again, this one, and this one are wrong. So 3 of them are wrong. But 32 minus 3, that's still 29. It doesn't look that bad. So, well, maybe it's a way to investigate.
May I comment your results?
Yes, please, because I'm playing with tools that I don't know, so
yeah, well, I
you're
can
the
see,
guru here.
Well, actually, you used completely wrong parameters for PickFinder 8, most probably, because 22 nanometers unit cell, meaning that you found a lot of peaks. So most probably you used very low SNR. So actually, that's a general comment for testing with Crystfel. First, you need to optimize very well your indexing parameters, all the geometry and everything, and then only you can compare. Otherwise, well, it's going to be not a very good comparison. And there are suggestions. So Tom just released recently Crystfel GUI. That's quite nice GUI for optimization of parameters. And he also released tutorial for this GUI. So if you want really to compare some results, try to use this GUI, look at tutorial, and he explains step by step what has to be done to process data. Don't hesitate to contact him, or you can also contact me because, well, I'm doing Crystfel for my living. That's
well.
Yeah.
Until last week, we were considering to present only the sparsification part, but because we managed to get something more or less running.
I don't blame you that you didn't do something wrong, but it's just, yes, things, if you want to continue like optimization of parameters, for example, for compression, then you have to do proper analysis. And also like looking at CC star, R split, it's all actually explained in Crystfel tutorial. But again, maybe it's not even your task. It should be somebody from ID 29, maybe Nicholas. I'm not sure who is from where, because users would need support. Exactly. You can't give users just, here is your data and try to do something. With XDS, it works. With Crystfel, unfortunately, not yet. And actually, one more suggestion, what you have shown with this found peaks, it's a very good start for online indexing. So Tom and Alexandra Tolstikova recently made several successful attempts to do online indexing. So they just were indexing crystals during measurements, both at Petra 3 and at XFEL. And you already did half of a job. So it's already like you almost there, because crystal can accept, I think, over ZMQ exactly what you found. So
actually,
it's just
we have implemented, so it's not directly in memory, but on ID 23.2, they're still running on a Pilatus, but we implemented this live pixeling, and we are trying to find a way to feed all the pics directly to Crystal via ZMQ. So this, I mean, we had a chat with Tom, so that's something we would like to do. Then we have to find a proper way to do that in the scale of our, cluster, infrastructure, and available resources, because Crystal is then CPU demanding, so we don't have access to thousands of cores at once just for us. That would be nice. So we have to find a way to balance, but that's what we're looking into. But thanks for the advice. And if maybe I'll contact you to see if you find ways to implement, because via ZMQ, because I'm looking for such things, because we are at a stage where we have the pics kind of live. We can follow up with the 250 Hertz on the Pilatus, but we would like to have feedback, direct feedback on the indexing, for example. That would be nice. We know it's possible, but the proper way to implement it, that's something we are looking into.
But you're right about resources. What we used was Maxwell cluster, where we have like up to 100 machines, 80 cores each. So it's something. Well, you don't need so much, but you really need a lot of computing resources. Here, you're completely right. So if you don't have those resources, it doesn't work really.
Yeah. Okay. Thanks.
So yeah, just to conclude with this tutorial, well, we have some advanced background analysis tool in PiFi, and maybe it can be used to compress raw data by discarding pixel of lesser interest. We have feature peak extraction algorithm that apparently is good enough since it allows indexing later on. The code is written in OpenCL. It has been designed to run at best on GPU, and especially NVIDIA GPU. Because this is what we have in our cluster. Even though I made the demonstration on an AMD GPU, and it didn't work always as smoothly as expected. Well, just as a simple rule of thumb, the GPU output is about 5 times the one of a CPU for the same price. Let's say if you put 10,000 euros in CPUs, you can have 5 times that performances by purchasing a GPU with the same price. Because the Vega 56 is maybe a not so common GPU, I put the table, and it compares more or less with an NVIDIA GTX 1080, which, yeah, in many sense it's similar. It has many more cores, but honestly it's less optimized, and the one that I'm using has a TDP of 150 watts, so it's not an overclocked version. It's yeah, and yeah, just to say that the code works on any brand of GPU. That's it for it, and maybe just one side comment. This peak finder tool was abused to perform the X-ray localization of crystals. When in MX, when you do X-ray centering, you can use this to reduce a 2D grid and to localize precisely where your crystal is physically. So this is an interesting side feature and it can be a replacement for Dosor, even if it does not exactly the same thing as Dosor does it, and it does it in a different way because the algorithm behind Dosor is not much published. But yeah, it's a way to localize precisely the crystals if you're interested. Well, with this, I'd like to thank you for your attention, and we have a bit of time if you have extra questions. So I apologize because well, I knew it was going to be very technical, but yeah, this is also an advanced tutorial, so yeah. You cannot do advanced science with simple things. Well, usually simple things have already been done. Yeah, Gudrun?
Hi. Jerome, do you think when you can extract all these peaks that one could somehow track them maybe through the images?
Yes, well, track them from
Also
one
then
image to the next.
Yeah.
Sorry.
Yeah, when I do scanning diffraction, then I think I would like to try this with just peak finder, but also maybe then, yeah, maybe it's then just by position. I don't know how to track the peaks along the scanning, if that's somehow possible.
I don't understand. I'm sorry.
Okay, so I'm scanning with the X-ray beam over my sample.
Yes.
Yes. And it has a diffraction signal. And then I would somehow like to follow maybe those peaks if they belong together or so. When I'm with the X-ray beam further.
That's a problem of isomorphism. You want to check if it's the same crystal.
Yes, maybe, yeah. I'm not such an expert there in diffraction, sorry. I'm just learning.
Well, if it's the same crystal, I would say it's likely that the position of the Bragg peaks are the same, or offsetted just by no, it should be the same. So you could count how many Bragg peaks are at the, let's say, co-located from one image to the next. You could imagine that, let's say, 80% of the Bragg peaks that you have recorded in image A and image B are at the same position. And
Sorry, Jerome, may I just answer a simpler question? There is a tool in Crystal which is called really gig. It's called, so it's actually doing exactly what you're asking. So it's searching for patterns with the same diffraction. Well, with diffraction, as Jerome said, with diffraction from the same crystals. It also can take into account if your crystal was a little bit rotated. So actually it just checks if positions of the Bragg peaks was shifted or not. So there is a tool in Crystal which exactly does what you want.
And now here's the tricky thing, because I do 2D scanning, X-ray diffraction. Will this work too? Do you think?
Yeah, it should work because, well, it just finds, it will spit you out all the diffraction patterns or numbers where the same crystal was observed. So it doesn't care if the images was one after another.
Okay, and also if in case I'm missing somehow rotation, because I only scan along as through the perpendicular through the image, I cannot rotate.
Right, but each your crystal is rotated in different orientation usually. Well, at least that's what people want to see, that every crystal is in different rotation. So it will find you the same orientation. Of course, if those are two crystals in the absolutely the same orientation, there is no way to distinguish, right? It's physically undistinguishable. But then there's, yeah, that's more difficult problem.
Could you maybe write down again the name into the chat, please, of the sub
program? Yeah, okay, I will.
Thank you so much.
You're welcome.
But Alexander, that works on indexed patterns, right?
Yes, sure.
Okay.
It's just you feed it the stream file, and then it gives you the output as a log file.
Okay. Thanks.
So yeah, without indexing, you could have a percentage of pixel of Bragg pics that did not move that much, but you would have to implement it yourself. And because Bragg pics are not ordered, before indexing at least, you have to consider the distance to the nearest each time. Well, maybe it's not that trivial.
What kind of material or sample are you scanning?
Hydroxyapatite.
Okay, if you don't have any more questions or comments, maybe it will be time to close this tutorial. I'd like to thank you all for your participation. Yeah, the poster session starts in 20 minutes, so it's just the time to have some refreshment before the poster session.
Yes. Thank you all.
Thank you very much.
Okay.
Thank you very much.
See you.
Bye.
Bye.